All right, in this podcast, we're going to talk about oxidation and reduction reactions, which are kind of combined and abbreviated as redox. All right, during redox reactions, electrons are transferred. Spontaneous redox reactions actually can transfer energy, and they can transfer this energy in the form of electrons through electricity or through the release or absorption of heat. Non-spontaneous reactions can be made to happen with electricity. Now, there is one thing I want us to understand here. Oxidation doesn't happen without reduction. Reduction doesn't happen without oxidation. They are coupled, so they occur at the same time. So to have one, you must have the other. Okay, so oxidation is the process by which an element attains a more positive oxidation state, meaning that it loses electrons. So you see in this example, it's showing you that the sodium metal is losing an electron and becoming Na1+. Reduction is when an element attains a more negative oxidation state, meaning that it actually gains electrons. So you see you have your chlorine gains 2 electrons and becomes this 2Cl-. All right, so there are a couple ways to help you remember what exactly happens in redox. One of them is Leo says Gur. So Leo, losing electrons, is oxidation. Gur, gaining electrons, is reduction. Or perhaps you might like this mnemonic a little better, oil rig. Oil rig stands for oxidation is losing, reduction is gaining. So either you're losing electrons or you're gaining electrons. All right, so a piece of iron is immersed in a solution of copper 2 sulfate. So we know that copper 2 sulfate is an ionic compound, so it is going to break into the Cu2+, SO4 2-. Because we're going from iron to iron 2+, that means we lost 2 electrons, so iron is being oxidized. Copper goes from copper 2+ to copper metal, so it is actually gaining electrons, so it is being reduced. All right, are all reactions redox reactions? No, absolutely not. Examples of redox reactions include single replacements, synthesis reactions, decomposition reactions, and combustion reactions. Non-redox reactions are going to be double replacement reactions or acid-base reactions. All right, so how can we tell what's going to get oxidized and what's going to get reduced in the actual reaction? We have to use these things called oxidation numbers. Oxidation numbers is basically a number that is assigned to an element which represents the number of electrons that is lost or gained by the atom of that element in the compound. And then you see a whole bunch of oxidation numbers down here. All right, so there are several rules for determining oxidation numbers. The first one is that the oxidation number of any atom in its elemental form is 0. So like magnesium, iron, H2, O2, Cl2, these are all diatomic elements. So that is how they naturally occur. Li, Cu. Okay, so any of these guys, their oxidation number is 0. All right, the oxidation number of any monoatomic ion is equal to its charge. So for example, Mg2+ has an oxidation number of 2+. Chlorine 1- has an oxidation number of 1-. The oxidation number of oxygen in a molecular compound is -2. Okay, so anytime you see oxygen, just go ahead and know that that is going to have a -2 oxidation number. Hydrogen, however, is a little different. It depends on what it's bonded to. So if hydrogen is bonded to a nonmetal, like in the case of H2O, okay, so H and O are both nonmetals, In this case, our H has a +1 oxidation number. And then if hydrogen is combined with a metal, as in the case of, say, lithium hydride, your hydrogen has a -1 oxidation number. All right, rule number 4, for any other covalent compound that does not contain hydrogen or oxygen, keywords here, the most electronegative element, so the one that is furthest right and further towards the top, has an oxidation number equal to its charge as an ion. So here we have BF3. We know that we don't have hydrogen or oxygen. Fluorine is the most electronegative, so fluorine on the periodic table has a charge of -1. So we're going to assign F a charge of -1 here. All right, and PCl3, again, no hydrogen or oxygen. Chlorine is the most electronegative, so it is going to also have a charge of -1 because it's in the same column as the fluorine. All right, the sum of the oxidation numbers for all the atoms in a compound must equal the overall charge of that compound. So, for example, here, if we were trying to determine this chlorate ion, ClO3, 1-. All right, so we see that it has a 1- charge overall. So that means that the sum of the oxidation numbers for this chlorine and this oxygen must be -1 because that's the charge of the overall. Okay, over here we have H2O. H2O is neutral. So that means that the oxidation numbers of the 2 hydrogens and the 1 oxygen must be 0, which is neutral. All right, so a little bit of practice. So let's find the oxidation numbers for all of these guys. Okay, so PCl5, Cl is the most electronegative, so that's going to be a 1- charge. So there's 5 of them. So 5 times 1-. P is kind of what we're trying to find here because we don't know it at this point. And overall, this is a neutral atom. So what this tells us is that P is going to be 5+ in this case. All right, SO3. All right, we got the O, so that's going to be 2-. There are 3 of them. And S is kind of our unknown. Again, a neutral compound, so we're going to set it equal to 0. So that means S has to be 6+. All right, here we have HI. Okay, so I is 1-, and H, because it's bonded to a nonmetal, is 1+. All right, barium 2+. Okay, it's a monoatomic ion, so the oxidation number for our barium is 2+. All right, N2. N2 is a diatomic element. All elements in their elemental state are 0. AgBr. Br is the most electronegative, has a charge of 1- on the table. So that means our Ag has to be 1+. And CaH2. In this case, we're bonded to a metal, so our H has a 1- charge. There are 2 of them. So that means that that's 2- for all the hydrogens. So that means calcium has to be 2+. All right, so let's apply oxidation numbers to some actual reactions. So we have to figure out which species gets oxidized and which gets reduced. So first thing you want to do is go around and assign oxidation numbers. So calcium, in its elemental state is going to be 0. Oxygen is going to be 0 because it's also in its elemental state. We know oxygen over here is 2-, and therefore calcium has to be 2+. So calcium goes from 0 to 2+. So what that tells us is that it is going to lose 2 electrons. And remember, whichever one you want to, however you want to remember it. But losing electrons is oxidation. So the calcium is definitely being oxidized. Okay, and then our oxygen is going from 0 to 2-. So it definitely gained 2 electrons, and reduction is gaining. So this is definitely going to be reduction. Okay, another example. Okay, so this one's got a little bit more going on. So just kind of start and see what you can get. All right, so we know this oxygen's 2 minus. That potassium has to be 1 plus. There are 3 oxygens. So 3 times 2 minus is equal to 0. I don't know what chlorine is yet. And I know that my potassium is 1 plus. So doing a little bit of algebra here, we basically have 5 minus on this side plus x, and my pen is jacking all up, is equal to 0. So that means that my chlorine had to be 5 plus. Okay, this one over here is a little bit more simple, this KCl. Chlorine's 1 minus and potassium is 1 plus. So we already see that chlorine is definitely changing charge here, changing oxidation numbers. So that's going to tell us that it's definitely going to be one of the species involved here. All right, we have H's attached to nonmetals, so that's going to be a 1 plus. Our oxygens are 2 minus in both these cases. There are 3 of them, so that's 6 minus over here. And then you still have your 1 plus, and we're looking for the nitrogen, all equal to 0. So that means that our nitrogen over here is 5 plus. And over here we have 4 minus and the 1, and still looking for the nitrogen. And that gives us 3 minus on this side, so our nitrogen had to be 3 plus. So it's our nitrogens and our chlorines. Okay, so chlorine is going from 5 plus to 1 minus. So that means that it is definitely getting more negative, which means it has to be gaining electrons. So chlorine is being reduced. Sorry about my chicken scratch there for a second. All right, and then my nitrogen is going from 3 plus to 5 plus, which means that it has definitely had to lose some more electrons, so it is being oxidized. All right, and last example. Okay, we have, well, let's do the easy parts first. So oxygen is just its own little element, so it has an oxidation number of 0. Sulfur here is the most electronegative, so it's going to be 2 minus, making that lead 2 plus. Oxygen's 2 minus, so lead is 2 plus. And then oxygen's 2 minus, 4 minus, so that means that sulfur had to be 4 plus. So the things that are changing here, it looks like the sulfur is changing and the oxygen is changing. Okay, so sulfur is going from 2 minus to 4 plus, which means that it is losing electrons. So that means that it is being oxidized. And then we are going from, for oxygen, we are going from 0 to 2 minus, meaning that it is getting more negative, so it is gaining electrons. I don't know where I wrote gaining there. It's supposed to be reduction, so it is being reduced.